Alright, welcome to today's class. So in our previous classes we've looked at the introduction to thermodynamics, and we've discussed some equipment or machines that uses the principle of thermodynamics, such as diffuser, nozzle, turbine, compressors, pumps, and the likes of them. So today we want to start solving questions. So the first question we have is on the screen, is displayed on the screen. So the question goes like this: a mixture of gases enters a nozzle at 2.5 bar. You can see this one is question on nozzle. So you first of all look at the particular machine that you are dealing with, or the question centered on. So this one is basically on nozzle. Is that taken? And the opposite of nozzle is diffuser. You understand? So you must know how to draw each one so that it will really help you in solving questions. So I already know some things that I must know. When I hear nozzle, one of the first things that will come to my mind is that the inlet velocity will be less than the outlet velocity. In fact, the outlet diameter will be less than the inlet diameter. Also, the area of the inlet diameter will be greater than the area of the outlet diameter. Alright, let's continue with the question. So since it is a nozzle, this is how my diagram will look like. Just a free body diagram. This is a nozzle. Is that taken? And one of the application of nozzle is to speed up the velocity. This is the inlet and this is the outlet, or we call it the exit. So the question says that the inlet, a mixture of gases enters a nozzle at 2.5 bar. Okay, inlet pressure, let me call it inlet pressure, P1 is equals to 2.5 bar. Alright, so and 237 degrees Celsius with a speed of 20 meter per second. So inlet temperature, that's T1, 237 degrees Celsius. Don't forget, for every temperature it will be converted to Kelvin, to degrees Celsius to Kelvin. We are going to add 237 plus 273. Is that taken? This will give 510 Kelvin. Okay, this one is the inlet velocity or speed. Let us call it C1, which is 20 meter per second. Okay, so the inlet diameter of the nozzle is 0.45 meter. Inlet diameter, which is, you can call it D1, 0.45 meter. Okay, it's in SI units. Now we are required to achieve an exit velocity of 340 meter. You can see, so V2 must be way greater than what? V1 for nozzle. D1 must be greater than D2. You are going to see by the time we solve this question. If you solve this question and realize that our D1 is less than D2, definitely we are wrong. So also the what A1 should be far greater than what A2. So the question said that outlet or exit velocity, you should achieve an exit velocity of 340 340, we call it C2, 340 meter per second. Okay, now assuming quasi-static flow condition through the nozzle. What does that mean? It simply means that the rate of change is that the rate of change of the property is considered to be very slow in order to be at the equilibrium. So quasi-static is a reversible process. It's a reversible process. So that's just it. Now we are now asked to calculate the pressure that should be maintained at the nozzle exit, that's P2, and the exit diameter, that is D2. Okay, we are looking for exit pressure, which we call P2, or no, exit diameter, which you call D2, is also unknown. So we are now given some conditions. What are the conditions? The condition is CP. Is that taken? So our CP is what's our CP? 1.15 kilojoules per kilogram per Kelvin. So CP is equals to 1.15 kilojoules per kilogram. Please know how to distinguish the K for kilo. This one is just what is telling you that multiple, but this one is a unit, someone's name, so it has to be written in capital letter as well as this. So that's just it. We are also given gamma to be 1.3. Okay, so we shouldn't forget, we have, for the gas, assume ideal and steady adiabatic flow through the nozzle. So we are asked what to follow the principle of what? Ideal and steady adiabatic flow through the nozzle. What does that simply mean? For a steady flow, it simply means that m dot, which is the mass flow rate, is equals to mass flow rate at the inlet must be equals to what? The mass flow rate at the outlet. Is that taken? So, and for the adiabatic process, that simply tells us that our Q will be 0, our W will be 0. Is that taken? And mostly for nozzle, is that taken? Our potential energy is always 0 unless stated otherwise. It's always taken to be 0, because your Z1 is equals to Z2, which is equals to 0, because your potential energy is equals to GZ, and like that. Now let's go back to solve the question. Okay, we've drawn the distance. So to start with, we have to find P2 and we have to find D2, the exit pressure and the exit diameter. Okay, if you go back to our steady flow energy equation, is that taken? The steady flow energy equation, we've realized that our Q is equals to 0, W is equals to 0. Okay, so from steady flow energy equation, what does this say? We have U1 plus P1 V1, don't forget this one is specific volume, plus kinetic energy. I'm using my velocity to be C, that will distinguish it from from volume. So plus GZ1 plus Q, is that again? So is equals to U2 plus P2 V2 plus C2 C squared over 2 C2 squared plus GZ2 plus, at the exit, work done will be produced. So we already know that our PE potential is equals to Q is equals to W, everything equals to 0. So we can now have this one to be, and also you know that our enthalpy is equals to internal energy plus the volumetric work or energy, which is P1 V1. So I can now substitute for this. I can take it to be what? H1 plus C1 squared over 2. This one becomes 0, this one becomes 0. Then this one becomes what? H2. Then C2 squared over 2. C2 squared over 2. Then all this becomes what? Becomes 0. Becomes 0. So as for this now, I can take this to the other side of the equation. Then I will have H1 minus H2 is equals to C2 squared minus C1 squared all over 2. Is that taken? But Cp T is equals to H. Is that taken? Because this, it occurs at constant pressure. Is that taken? So that's the reason why we have what? H is equals to this. So as we now have it now, we can now have this to be delta H, which is change in enthalpy. You can see change in enthalpy here is equals to Cp, which is constant. Now this one is now T1 minus T2. T1 minus T2. For this one comes first, H1, so it is T1 that will be here. Now this one, then we are going to have T2. We can now substitute into this equation. Let me put this one equation 1 and this one equation 2. So this one, you now say that what? Put H2 for H1 minus H2. So as we now have it now, we can now have a change in H, as in change in enthalpy, this minus C1 squared over 2. Okay, so in this case now, we can simply have this, that is Cp into brackets T1 minus T2, which is the temperature, then C2 squared minus C1 squared over 2. Do you understand now? Now here we are given T1, we don't have T2. Okay, let's look for T2. Is that taken? So if we look for T2, from there we can now go and look for our pressure from the adiabatic, the general formula of what, or the equation for adiabatic. So here I can have my, if I'm to substitute, I've been given my C2 to be, what's it called? Okay, or better still, let me divide both sides by this. I have T1 minus T2 is equals to C2 squared minus C1 squared divided by 2Cp. So on substitution, what will I have? This, it has been given in the question, C2. What's our C2? Our C2, that's 340. Our C1 is this. Then our T1 is 510. Okay, we are good to go. So in this case, this one is 340 squared minus 20 squared divided by 2 into bracket our Cp. Our Cp, I think 1.15 kilojoules. Now you have to be very careful. So here in this formula now, kinetic energy is expressed in joules. You understand? So we are going to convert the kilojoules to joules. So our Cp that's given has 1.15 kilojoules per kilogram per Kelvin. we now multiply by 1000 kilo. If you multiply this by 100, we have 1150. Okay, this one have 1150. Now let us use a calculator. Come in. Using calculator, we have 340 squared minus 20 squared divided by 2 divided by 1150. Then I have 50.086. Alright. This one is equals to 50.086 in Kelvin. Okay, 69. Let me put it to be 7. Better still, this one is 9 in Kelvin. That's our temperature. So in order to further with our solution, now we can this. So T1 minus T2 has given us 50.09. So since we are looking for T2, we can take that as T1 minus 50.09 is equals to T2. So here, what is my T1? My T1 was 510. I don't bother myself. It is 510 minus 50.09. So minus 50.09 minus 510. So we have 459.91 Kelvin. So approximately our T2 is equals to, let's say, 460 Kelvin. That's our T2. That is our T2. Okay, move to the next page. So here, the second condition we are given is quasi-static adiabatic condition flow. You understand? So in that case, I told you that for a quasi-static adiabatic condition, it is, as in the rate of change is very slow. Is that okay? So it can be considered steady flow. You understand? So in this case now, because of the adiabatic, so for isentropic, as it is adiabatic, it is what? Isentropic. For isentropic flow, you know that PV gamma is equals to C. Is that again? I can now have my P1 V1 gamma is equals to P2 V2 gamma, isn't it? Okay, let us quickly derive this, because here we are not given anything related to volume. Okay, since it is an ideal gas, is that again? You also know that PV is equals to this one in this case now is capital letter, this one is small letter, specific volume, this one is actual volume, MRT. You understand now? So if you now have PV capital letter M over small letter m is equals to RT, where small letter V, which is specific volume, is equals to capital letter V over M. You understand now? I can now have my P small letter V is equals to RT, where I have here. You understand? Let me make the small letter V the subject. I will now have small letter V is equals to RT over P. You understand? Please take note of that. Take note, kindly take notes. Let me change, I think I should change the color. Is that okay? Okay, I want to change the color. So in this case now, we should now call this one equation 2, and this one is equation, what's it called? Equation 1. Okay, fine. So here you put RT over P for V, for every V that you see here. So it changes the equation to be P1. What is my V1 now? Is now what? RT1 over P1, then gamma is equals to P2, which is RT2 over P2, then gamma. Okay, so in this case, don't forget that the R is constant. Is that okay? So using law of indices, you will have this to be P1, because law of indices, this one divided by this one, whereby this one has gamma, it will now be 1 minus gamma. You understand now? So to bracket R raised to power gamma, then T1 gamma is equals to, same thing goes with this, P2 1 minus gamma, then we have R raised to power gamma, and finally we now have T2 gamma. Is that okay? So in this case now, this one and this one, they can come together, they become what? Constant. You understand? We can remove them. So here we can finally have seems this red makes more sense than this other color. Okay, so in this case, then I will have P1 raised to power 1 minus gamma, then T1 gamma is equals to, exactly what I'm saying is this cancel this, you understand? Then is equals to what? That is P2 raised to power 1 minus gamma, then T2 gamma. Okay, let us bring them together by the like terms. So I can now have my P1 over P2 raised to power 1 minus gamma, isn't it? Then I have this one comes here, then this one will come to the other side, then T2 over T1 raised to power gamma. You understand? So we finally have this. We're going to have this, or we get it as T1 raised to power gamma. This one, if you want to change it to reciprocal, it becomes P1 plus gamma minus 1 is equals to T2 raised to power gamma, then P2 gamma minus 1. So you have both equations are valid. You understand now? So we can now look for our P2 that we are looking for. So in that case, okay, can look good for that. So according to this equation now, you understand now, if you want to remove this, is that taking, you know, this is power, I'm going to root it with this. So you now have P1 over P2 is equals to T2 over T1 raised to power gamma over 1 minus gamma. Is that taking? Now let us quickly look for gamma. Look for the value of gamma over 1 minus gamma. What's going to be the value? Our gamma is 1.3. Then 1 minus 1.3. This one gives 1.3 over 0.3. So using our calculator, we have 1.3 divided by 0.3. We are going to get 4.33. It has no unit, 4.333. Anyhow, it's continuing like that. So the next thing we are going to do is to make P2 the subject of formula. So here we have P1 over P2 is equals to, what is my T1? My T2. My T2, we've calculated T2, which is 460. I can use 460 directly. 460 over T1 is 510 raised to power, which is gamma over this, raised to power 4.333. Is that taken? So doing that, I have 460 divided by 510 So this one gives this divided by this gives 0.90196. So answer raised to power 4.883. So this gives 0. So we are going to have our p1 over p2, okay, raised to power 4.333 here. So you finally have when you raise this on to power of this, then you are going to have 0.63948. So making p2 the solid of formula, so we are going to have p1 multiplied by 0.63948 multiplied by, okay, multiplied by 1 is nothing, so is equals to p2. Is that taken? So by multiplying, what's our p1? Our p1 is equals to what was given in the question. The p1 was 2.5, isn't 2.5? Yes, 2.5 bar. Yes, it was 2.5 bar. So you now say that 2.5 multiplied by 0.63948. So finally, you are going to have 2.5. So finally, you're going to have 1.599 bar, which can be approximately 1.6 bar as the pressure, the outlet pressure. And that was the first question we have to find. So what is expressed here? Okay, now the next question is now that we should find the diameter. How do we find the diameter? To find the diameter of the outlet. So in order to find the diameter, we must look for some other things before it will lead to diameter. Because one of the equation we are going to use is, number one, we are going to use continuity equation. As far as mass flow rate is concerned, since the mass flow rate of the input must be equal to the output, because it is a steady flow condition. So in that case, so here now, since we are considering an ideal gas, so since we are considering an ideal gas, like I said earlier, PV is equals to RT, where V is equals to V over M. You understand? Okay. So in that case now, let us look for the specific volume of inlet. The specific volume of the inlet, now using this formula, anything associated to the inlet will be P1, V1 and the likes. You understand? So in order to look for the specific volume of the inlet, we are going to have V1 is equals to RT over P1, then T1 here. But now we only have CP. We did not have what? We did not have our R, because it wasn't given from the question. Is that again? But there is a way that we can look for our R. How? CP minus CV is equals to R, and also CP over CV is equals to gamma. You understand now? So if we substitute here and make gamma the solid of formula, make CV the solid of formula here, we're going to have CP over gamma is equals to CV. Now I can now put it here. What is my CP minus CV? That is CP over gamma over gamma. is equals to my R. You understand? Now let me evaluate. So this one will be 1.15 as it was given in the question. 1.15 is that taken? So this is gamma. It's just saying that this times this, that is Cp gamma minus Cp over gamma. So I will multiply by 1.3, then I will have over gamma here, which is 1.3. So here I can now have my this to be 1.3 multiplied by 1.15 minus 1.15, so then divided by 1.3. Finally I will have my CV to be that. Okay, my R is now, my R is going to be, so I've gotten my R to be 0.265. Okay, let me put it 4 approximately. This one is kilojoules per kilogram per Kelvin. I can convert it to joules. That will be multiplied by 1000. That's 265.4 joules per kilogram per Kelvin. So that's going to be our R. So we are now going to use it in solving the question. So here, to go back to, so here we'll now have our V1 is equals to, what is our R? That is 265.4 multiplied by T1, that is 510, divided by P1. What's our P1? That is 2.5 bar. Is that taken? 2.5 bar. So we have to take it to what's it called, Newton per meter square. Is that taken? So which is, we are going to multiply by 1000. Is it that you take it to Newton per meter square, you take it to Pascal? They both have the same value. So you multiply this one by 100,000. Sorry, 100,000. Multiply this by 100,000. So here I can now have my this as it. So I have 265.4 multiplied by 510. Beautiful. Now divided by 2.5 divided by 100,000, which has 5 zeros. Am I correct? Then I have my specific volume for 1 equals to 0.54. So my V1 is equals to 0.54. Now this one is now what? Specific volume. That is meter cube per kilogram. Don't forget specific volume. So we'll do the same thing for V2. For V2, which is the outlet, we're going to have R remains the same. It is 265.4 multiplied by T1. What's our T1? That is 460. Let me confirm. We calculated it. Okay. Yes, it was 460. Okay, and see that that's 460. Now divided by same thing. No, what is our P2 now? Our P2 was, we calculated it, our P2 is 1.6 bar. 1.6 bar, so must use the value appropriately. So this one is 1.6 bar. 1.6 multiplied by 100,000, like I said the other time. So we're going to have 265.4 multiplied by 460, which is the temperature, divided by 100,000 divided by 1.6. Then finally you have 0.76, that is meter cube per kilogram. Beautiful. Now we now apply continuity. from continuity equation. So since m dot is equals to m1 for a steady flow, is that taken for steady flow, what does that mean? It simply means that what the mass of the gas that enters at the inlet will also be the same quantity of what of gas that will come out at the outlet. That's just the meaning. So here we also have that mass flow rate is equals to AC over specific volume. That's the reason why we have to calculate this. Now, what are we really looking for? We are looking for diameter. We can get the diameter since we have our area. That's the reason why we have to calculate this. Okay. Before that, we don't know this. We know the diameter for the inlet. We know the the speed for the inlet, and we also know the mass flow. The specific volume for inlet. So for inlet, so m dot 1 is equals to a1 then c1, which is the velocity, and specific volume 1. Now if you do this now, our a1 is equals to pi d squared over 4. So that's 3.142 multiplied by what is our temperature at the inlet. It was given to be 20 squared. Sorry, I was looking at this. So this one, diameter at the inlet was what? I think 0.45 or so. Let me confirm. Yes, 0.45. 0.45. The inlet diameter is 0.45. So this one is 0.45 squared divided by 4. Using our calculator correctly, 3.142, which is the pi, multiplied by 0.45 squared, then divided by 4. I'm going to have 0.159 approximately. We'll have so this one 0.1591. So this one is meter squared. Since it is area, now let us come here to substitute. This one is now 0.1591 multiplied by 20, which is the velocity. Is that taken? So this is the velocity. Now specific volume for 1. What's the specific volume for 1? That's 0.54. So use it, 0.54. Now let us calculate that. It is okay that I got recently, multiply by 20, then divided by 0.54. I'm going to have my answer to be 5.89. What's the mass flow rate? It is kilogram per second. That's the unit. So since m1 is equals to m dot 1 is equals to m dot 2, since m dot 1 is equals to m dot 2 as a mass flow rate, so I'm going to have this one to now be a2 c2 over v2. Now if I'm to substitute now, what's going to be my a2? I don't know. My c2, we have it to be 320 over v2. That's what we calculated earlier. v2 here is this 0.76. so 0.76, you come here, you put 0.76. so what's our mass flow rate? Our mass flow rate is 5.89 is equals to a2 multiplied by 320 divided by 0.76. you cross multiply. Our a2 is equals to 5.89 multiplied by 0.76 divided by 320. So doing that, I have 5.89 multiplied by 0.76 divided by 320. And finally you have this to be 0.01399. Is that taken? This one is meter squared. Okay, now since we are looking for the outlet diameter, but area is equals to pi d squared over 4. Is that taken? So area 2, this one will now be what? 4a2 is equals to pi d2 squared. So d2 squared will equals to 4a2 over pi. Is that taken? So finally my d2 will equals to square root of 4a2 over pi. Is that taken? Then I'm going to substitute 4 times area 2, which is 0.01399. Then what's this? Pi. That's 3.142. Then to do that, you will have a square root of multiply by 4, then divided by 3.142. And finally, what will I have? I'm going to have 0. I will have 0.133 meter. 133 meters. So always express your answer in sentence form. Therefore, the outlet pressure and diameter what's the outlet pressure? What did we get? We had 1.6. Yes, 1.6. We had 1.6 bar and 0.133 meters respectively. That's your answer. And don't forget to check if what you did was correct. Confirm if your diameter, the outlet diameter, which is D2, is that taken? The outlet diameter must be less than D1, and we can confirm that our D1 was 0.45. So this one, D1 is greater than D2, correct in that aspect. And also C2 must be far greater than C1, which is equals to 320 is far greater than 20, so it is correct. That's how to confirm if your answers are right or wrong. Thanks for watching. Follow for more questions and solutions like this. Thank you. Don't forget to like, share and subscribe. You press the follow button. Thank you.